Just like you need to graph all of your exponential functions, we are going to graph every single log graph and do all the transformations with that as well. So one of the expectations is that you will see y equals log base 4 of x and think of the graph immediately. Right now that might not be the case. So a little bit of background of how you can figure it out. Eventually I hope you don't have to do the background part. But logs and powers are inverses. So y equals log 4 of x is the inverse of y equals 4 to the x. And if I can graph 4 to the x, because that's something that we've graphed before, right? All exponential graphs have the point 0, 1. And all exponential graphs would have the point 1, 4. And this is the shape of y equals 4 to the x with an asymptote at y equals 0. And if we go back to chapter 3 and we think about inverses, what did inverses do? They just switch the x and the y coordinates everywhere. So now if I want to graph y equals log base 4 of x, well, instead of 0, 1, we're going to find out that all log graphs have the point 1, 0. Just like all exponential graphs have 0, 1, when you switch x and y, that means all log graphs are going to have 1, 0. And if I had the point 1, 4, you're going to have the point 4, 1, which kind of makes sense. If you plug in a 4 for x, 4 to what exponent would be 4? The answer would be 1. Even the asymptote has the x's and y's switched. So we have the asymptote. It's at y equals 0. If you switched x and y, well, the y would become an x. And then you would just have x equals 0. And this is the shape of every log graph. And we're going to do all the transformations with log graphs as well. So stretches, compressions, move it left, right, up, and down. And the key to being able to do that is you need to know what the parent graph looks like. So from now on, I'm hopeful you can, if I give you a log base 7 of x graph, you'd be like, it has 1, 0 and 7, 1. And you'd be able to graph it, and then use that if you had any transformations to do any new graphs. Okay, it asks for some information. So it has an x-intercept at 1, 0. But because of that asymptote, there are no y-intercepts. Here's your asymptote at x equals 0. The domain, x is bigger than but not equal to 0, and your range is everything. Questions for practice on this one are 10 and 11, but I'm going to get you to graph one more graph. So I think you have space still on page, at the bottom of page 378. I'm going to introduce you to ln of x. ln is French for natural logarithm. In French, it's logarithm naturel or something very much more well-defined and pronounced than probably what I did there. But that's why it's L first for logarithm and N for natural. And you know how, you remember that this one was called the common log? And this is going to be called the natural log. The common log, when you didn't write anything, had a base of 10. The natural log, I'll write it here, natural log of x is the same as writing log with the fancy number e. Remember that fancy number e we got introduced to the other day? 2.718281828, and then another number, and then another number. And the natural log happens so much in calculus, like you don't even use a common log once you get to calculus. It's almost exclusively natural logs when you get to calculus, because they just naturally have better qualities than the other logs. But if I were to graph this, well, all logs have the point 1, 0. And since the base is e, the natural log would have the point e, 1. It would still have the asymptote at x equals 0. And it would have this shape.